So,
3:15.
yeah, I think we should start. Okay, so thanks a lot. Just arrived from the airport. We would like Carlos Arguelles to be here, and he's going to be talking to us. So this is the third course of the school here about astrophysical neutrinos. So thank you, Carlos.
Yeah, it's wonderful to be here and meet you all. Hello. So what my plan today, or this series of lectures, is to talk about neutrino detectors for high neutrino astrophysics, techniques that we use to detect these neutrinos, and I want to give you an overview of what's going on with high neutrino astrophysics. And my background is actually not on astrophysics. I'm a particle physics by formation. So you will see that I tend to fall back into particle physics language very, very often. Nope. Okay. So the objective of this lecture series is to be complementary to what you've heard last week. I imagine you have talked about gravitational waves, and you have talked about gamma ray observations. And the idea is to look at this third window of the universe, which is neutrinos. And I want to be more specific about my goals and expectations. I want to, oops, let me see if I move this here. Yeah. I want to be able to give you enough tools so that when you go to, for example, the IceCube website, which is one of the experiments that we're going to talk about. In fact, we're going to predominantly talk about IceCube. You can go to the IceCube website, and then you can look at our data releases. And these data releases are actually quite frequently updated. And the idea being is that you can produce your own analysis. Similar other experiments, which I will comment later, have also open data sets. And so my vision is that with the tools of this series of lectures, you can go to a website and you can do some science by yourself. So that's our end goal. And wait. Okay. So it's a long series of topics that I want to cover in this series of lectures. So today and tomorrow, I want to talk about why do we do high-energy neutrino astrophysics. I want to talk about some history in what were the paths towards neutrino astronomy. I want to talk about the signatures, backgrounds, and particle physics that's necessary to understand these signatures. And then I want to tell you how, now about 10 years ago, we discovered high-energy neutrinos from outer space. And then after the first two lectures, I want to do a statistics interlude, where I'm going to tell you some statistical techniques that we use in neutrino astrophysics. Then I'm going to talk about neutrino sources based on this. And then I'm going to have a second interlude, where I want to talk about how neutrinos change flavor as they travel, because that's going to be a very important property to talk about particle physics of high-energy neutrinos. And then I'm going to try to wrap it up. This is my objective. Hopefully, we'll cover many of these topics, but the most important part is that you all ask questions. It's better that something's sinking really well rather than we cover as much material as we have. Okay. The space of it's very narrow. So let me talk about motivation of why doing neutrino astrophysics. Maybe I will just stand here. So in reality, the first observation of extraterrestrial neutrinos outside of our solar system was in about more than 30 years ago. In 1987, there was a supernova in the Large Magnetic Cloud that exploded. And it was seen by 3 experiments, Baxan, IMB in the US, and Kamiokande in Japan. And so this was, in a very broad sense, the birth of high neutrino astrophysics. But these are actually not the neutrinos we're going to be talking about. When we talk about neutrinos that are significantly higher energy than neutrinos, these neutrinos are typically orders of tens of MeVs. And so the motivation to do high-energy neutrino astrophysics is to try to resolve the puzzle, the following puzzle. And as you may have heard last week, one of the oldest problems in astroparticle physics is the origin and acceleration mechanism of high-energy cosmic rays. So high-energy cosmic rays, they cover a broad range of energies. So in this plot, here is the energy of the particle, and here is the intensity. And so you can see that we managed to produce particles that are all the way to 10 to the 20 electron volts at a high, quite significant luminosity. So the question is, how do we do this? Or how does nature do this? So to give you a sense of scale, the highest energy cosmic rays observed was seen by fly eye about 30 years ago, and it had this much energy. I'm not going to say the number of zeros, but it's a very large number. And if you want to do that with an anthropogenic accelerator, so something that we could build here at Earth, you will need to have an accelerator that roughly has the diameter of Mercury. So somehow nature does this for us. And so this is my one slide on how accelerators work. And I know you have talked about in much better detail last week. And so the idea is that there is some kind of cosmic accelerator that maybe is powered by gravitational forces of a large black hole. And that is accelerating protons. And those protons are impacting material or radiation around the black hole. And in that, they are producing particles. And those particles are going to, if they have electric charge, they can be bended by local magnetic fields or magnetic fields along the way. Or if not, they can just come out of the source. And so the particles that are going to be interested about are pions. For example, if you have proton-photon interactions, you can produce neutrons plus pi pluses. Those pi pluses unavoidably decay, making neutrinos. And then you also are going to get pi gamma production into protons pi zeros. And these pi zeros are going to make gammas. And so the production of neutrinos and gamma rays in these objects are meant to be correlated. We're going to see later this correlation is not so simple, but they are entangled messengers. Okay? Oh, that worked. So this is my cartoon of one of these objects. It's shooting high-energy particles out of it. There are protons that are produced from these high-energy accelerators. But protons are actually deflected by magnetic fields, either at the source or in the extragalactic medium. And they actually, when they arrive to Earth, they no longer point in the direction of the accelerator. Gamma rays, of course, they're not deflected by magnetic fields. They can go in a straight line. However, gamma rays are going to be attenuated at very high energies. And the reason is that of a certain critical energies, you can have that high-energy gamma ray can interact with the CMB, producing a pair of E plus, E minus. And that's going to make the universe essentially non-transparent to high-energy gamma rays. And this is what neutrinos are going to enter. So you can see this in another way. So this is the energy of my messenger, very broadly defined. And this is the distance of observation. And so what's, let's say, transparent is something that we can see. So we can see microwaves, optical light, X-rays, gamma rays, all the way up to these energies. But as I was saying earlier, when you have high energy gamma rays, these actually can interact with the CMB, making the universe no longer transparent to light. This is where we believe this is revealed only by neutrinos or gravitational waves or high energy cosmic rays if they are boosted enough. Okay, so this is the land that we are trying to uncover. So the motivation for neutrino astrophysics is quite simple. They are electrically neutral particles, so that means that they are not going to be deflected by the magnetic fields between the sources and us. So they're going to actually point to the source of cosmic rays. They are going to be massless, so they're going to come essentially on time. They're going to be unabsorbed, and that's because the neutrinos are actually only going to interact via the weak interaction. And that means that if I have high energy neutrino, it's actually going to be able to traverse the size of our observable universe. And if we are able to see these neutrinos, they hopefully reveal the sources of cosmic rays, or maybe they reveal something that we know about. Maybe something totally unexpected is in that dark regime. But there is a downside. The downside is that because they are unabsorbed, the cross-section is very small, they're very difficult to detect. So you need a very large detector. So the question is, oops, let me go back. How large of a detector do you need? Oh, I'm going the right direction, yeah. So there's a calculation that you could do that was done in the 60s. So this is the intensity again, this is flux, and this is energy in wavelength. And so you can see here you have the high energy cosmic rays. These are the highest energy radiation in the universe. And then you have the CMB, which is the most abundant one, but it's lower energy. So what you could have is you could have one of those very high energy cosmic rays, for example, one of these ones, interact with one of these CMB photons. And in that interaction, you could produce neutrinos. You can have a proton, for example, make a hit with a CMB photon, making a charged pion, and that's a neutrino. So you can make a calculation, and you know this flux, you know this flux, you know this cross-section, so you can more or less figure out the order of magnitude of this neutrino emission here. And this is known as the GCK neutrino flux. And essentially it's the traditional motivation of neutrino astronomy. And so this was already known in the 70s. So I'm going to go in more details about this, in actually quite glory details. But when you do this calculation, you figure out that the cosmic rays start disappearing, and neutrinos start appearing at energies close to 1 exa-electron volt. That's 10 to the 16 TeV. A TeV is 1,000 GeV. A GeV is the mass of a proton. And then you can compute the flux of those neutrinos. And then you will figure out that to get about one event of these neutrinos, you need a kilometer scale detector. But if you manage to build this, this is one that actually points back to the source. Okay. Any questions so far? Okay. So the idea by Markov in the 60s was that maybe we can install detectors in lakes or natural mediums as a sea, or later will be a glacier, where we could observe radiation produced by charged particles, known as Cherenkov radiation, to observe these particles. So that's the motivation. That motivation has, now grown. I think that now that we have seen neutrino sources, and we'll talk about more later, that is now a whole area of research. So now we still have even more motivators, but that was the original, let's say, tale of this story. And this story has lots of pioneers that I want to acknowledge. I am a person that likes history a lot, so maybe you also enjoy that. This is the only history I'm talking about in my lectures. My PhD advisor used to tell me that history is for all people. We have to look at the future. But let me just tell you what the history was. So the first ideas to build these kind of detectors come from a collaboration as the Dumant project for deep underground muon and neutrino detector. This collaboration operated for about 20 years. This is one of their earliest cartoons. You can see here the seabed. This is the Dumant array. Yes, it's a little cube called Dumant. And the idea is that they will observe these neutrinos. Now, let me tell you that in those days, people didn't actually know the masses of the particles. Those days, people thought that the W boson, for example, was around 5 GeV mass. Now we know it's about 80. So the particle physics was very optimistic, how long this will take to do. Dumant, this is something that happens, unfortunately, to many, at least particle physics projects, is that you start with some idea. They wanted to build a 1 cubic kilometer detector. This is what you needed for the back of the envelope calculation. That required about 20,000 optical sensors. We're going to talk about more what those are in a minute. But then reality kicks in. It means funding agencies. And so then they say, no, you cannot afford this, so you do this size, then this size, and then this size. And so in the end, they managed to get money for this, it's a starting position. About 200 of these sensors, the starting block. And this sensor was actually deployed off the shore of Hawaii, and it was called the Triad detector. There were 3 strings. Unfortunately, they deployed it and very promptly stopped working because water started leaking in and things broke. So that was bad. And then the demand collaboration sort of split for multiple reasons. First of all, because of this failure of this device, but also because the Cold War was not a good time for collaboration between US and Russia, and things sort of split into multiple pieces. So one group, the Russians, they went to Russia. And there is a place called Lake Baikal in Russia. It's one of the highest altitude lakes that exists in the world. And they deployed something like the Baikal Neutrino telescope in the 90s. It was building on the technology that was developed for demand. And it had these optical sensors. These are actually photomultiplier tubes. So they are sensors that are able to convert light into electric charge. And they have this in this sort of like pair motion. And so what's very interesting is that the Russians actually were the first people to be able to actually reconstruct neutrino events in this sort of technology. So in 1996, they were actually able to see a neutrino in their detector. This neutrino was not produced in an astrophysical source. It was actually produced in the Earth atmosphere. We'll talk about these neutrinos later, but these were the sort of pioneers. Another group of people went in a different direction. They went to Antarctica and built something known as AMANDA, which stands for Antarctic Muon and Neutrino Detector Array. And AMANDA had several phases of construction of AMANDA 1 and AMANDA 2. And AMANDA was roughly 500 meters in height. And they were also able to observe neutrinos. This is one of the events in AMANDA. And what was tricky about AMANDA is that first they deployed it this is the depth, essentially. And this is the scattering coefficient, so in inverse meter, which means that the larger this is, the more transparent the medium is, and the smaller it is, the more opaque it is. And so you can see that here in the surface of the ice, it's kind of opaque, and as we go deeper, it becomes more and more transparent. So they have to optimize the location in a couple of attempts. But eventually, they managed to see at least atmospheric neutrinos. This collaboration will later become the IceCube neutrino collaboration. And then there is another group of people that went to the Mediterranean Sea and built something known as Antares. And though that detector looks like this, also had photomultiplier tubes in tandem. And that detector actually operated, so this was set actually last year, and managed to see atmospheric neutrinos, but no astrophysical neutrinos. And this experiment also had a second generation, which we'll talk about in the next lectures, called KM3net. And so these are, again, part of the pioneers. Okay. Oops, back. So that's all the history I want to tell you. And if you're really interested in this, there are these 3 nice references. This you have to pay, but you can get in the library probably. But this one is free. And this is actually a really nice review about the history of neutrino astronomy. It's a really, really fun read. This one actually, it's written by a reporter that actually went to the South Pole with the people that installed the detector. So it's a very colorful story of the detector. This is a more general neutrino book discussion. Okay. So now I'm going to talk mostly about IceCube, but later I will talk about water detectors. And the reason I'm going to talk about IceCube is because IceCube is currently the largest operating neutrino observatory. I'm also happen to be an IceCube neutrino observatory member, so I'm very biased here. But many of the techniques that and concepts that I'm putting here transfer readily to water detectors. Okay. So the IceCube Neutrino Observatory is in Antarctica. So here we are in Sao Paulo. By the way, these images are up to scale, just so you can see the size of Antarctica with respect to South America. Usually when I show these sometimes in the US or Europe, it looks much larger than Antarctica, but South America is actually quite a large subcontinent. If you were to go there, you will find this building. This is the IceCube computer center. It's going to host the computers that are going to process the data recorded by the detector. And then underneath this, you're going to find our sensors. I'm going to see if this works, but sometimes this is finicky video. But essentially, the detector was deployed about 2.5 kilometers deep in the ice using a hot water drill. And the procedure is you first put a first probe that has a weight to start the path that you want your hole to be drilling. And then you replace it by this object here. This actually is pumping it hot water at high pressure. And this has to go 2.5 kilometers deep in the Antarctic glacier. And this is actually fueled by power plants operating in the South Pole that uses jet fuel. So this is quite of an engineering feat to actually be able to do this deployment. And let me show you how this looks. Oops, here. So this is the IceCube Neutrino Observatory. It is embedded in the Antarctic glacier. Antarctic glacier around the South Pole is about 2.5 kilometers tall. The Antarctica has actually bedrock, or so it's a continent below it. And the whole glacier is sliding slowly over the rock. The detector is comprised of these strings. Each string is going to contain 60 sensors. And the sensors are going to be spaced out about 70 meters vertically. And the strings are going to be spaced out about 125 meters horizontally. Altogether, as you could suspect, this is about 1 cubic kilometer of very Antarctic ice, very clear Antarctic ice, which roughly corresponds to 1 gigaton of target materials for the neutrinos to interact. There are other parts of this complex, so I'm not going to talk in my lectures, but I will just point them out for later references. One is IceTop, which is a cosmic ray detector that's built on top of IceCube. And the idea is that under some situation, I'll show you one event display later, it can veto events that have coincident cosmic rays coming at the same time as neutrinos from this particular direction. And then it has a sub-detector here called Deep Core, which is embedded in the innermost part of IceCube. And it's comprised of a more tightly packed array that's designed for low energy physics, in particular for neutrino oscillation physics, which we'll talk about later. Okay. Overall, there are 5,000 of these sensors deployed in the ice. So what do these sensors look like? Each of these sensors has one photomultiplier tube. It's a 10-inch PMT. And the photomultiplier tube converts essentially Cherenkov light into electric charge. And the thing that's important is D here for digital. And that means that once the Cherenkov light hits this, the PMT records a signal, that signal is digitalized in situ in the dome location. So that was one of the biggest changes between this, let's say, second generation detector and the previous detectors I was telling you earlier, like Antares or Baikal or Amanda. Those use optical modules. That meant that the signal from the PMT actually went up the wire to a station up north. But the problem with that is that caused signal degradation. And so the breakthrough with IceCube was to make the signal digitalized in situ to avoid signal degradation. And essentially now every single neutrino telescope that we have operating or being under construction operates with a digital system. And like I was mentioning, they are put in this array of detectors. Okay, so how do we see neutrinos with these objects? Well, let me tell you a little about how neutrino interacts, because just to put some language, some common language together. So I'm not sure how many of you have taken particle physics, but this is going to appear lots of time in this talk, so I'm just going to say it once. This is a Feynman diagram, and so here in the horizontal axis there is time, and this is position. This is meant to be more like a schematic than a real representation of the interaction. But we like to think in particle physics as interaction between particles as an exchange of a mediating particle. So for example, here you have a neutrino that interacts with a d quark, for example, instead of a proton, and the interaction is mediated by the exchange of a C boson. And so this looks like a normal billiard ball scattering. Neutrino comes in, the quark maybe stays, and neutrino comes out. But the neutrino has other special type of interaction, which is known as a charge current neutrino interaction. And this interaction is very special because in this interaction, the neutrino actually changes identity. So you can have an electron neutrino interact with a d quark, but this time, instead of exchanging a C boson, it exchanges a W boson. And then the neutrino converts itself into an electron, and the D converts itself into U. So now we have an identity change from a neutrino into a charged particle. And the same is going to be the case for the mu neutrino and the tau neutrino. In fact, these interactions is what defines what we mean by an electron, a muon, and a tau neutrino. We mean that an electron neutrino is a neutrino such that when it interacts via charge current exchange, it produces an electron. A muon neutrino is such that when it interacts via charge current exchange, it produces a muon, and then a tau neutrino equivalently produces a tau. And in the standard model of particle physics, the neutrino and its corresponding charge partner, as we call them, are actually intimately related in the theory. So these charge current interactions are going to be detected by neutrino observatories. Typically, muon neutrino interactions can be observed when the interactions happen in the detector or around the detector, since these muons are actually going to travel significant distances. Electron neutrinos can be seen when the interaction happens inside the detector or in the vicinity of the detector. And then tau neutrinos can be identified on an event-by-event basis when they interact inside the detector. And I will tell you exactly how this happens. So we're going to start talking first about mu neutrinos, since this is the, say, workhorse for neutrino astronomy. So the idea is that you have a neutrino. It's coming perhaps to the planets or maybe horizontally. And it interacts in the ice, or it could be water if you're in something like internet. And it makes a muon. And that muon is going to travel in the ice. We're going to talk about particles that have energies of TeV and higher. So these are all very high energy particles. And when you have a high energy muon in ice or in water is going to emit Cherenkov light. And that Cherenkov light is going to have a particular shape that depends on the medium. And so what we can do is we can look at the arrival of light at our sensors, and using the time and arrival of light, figure out the direction of these events, and this can be typically done with quite good precision. Now, the other morphologies are going to produce different light patterns. And so, for example, muon neutrinos are going to produce high energy muons, and high energy muons are going to go through the detector. And let me, for a second, explain what this means. So here you can see these vertical lines. There are little dots in those lines. Each dot corresponds to a photosensor. When the photosensor has seen light, we put color in it. And so the larger the sphere that we put on it, it means it has seen more light, and the smaller the sphere, it has seen less light. So for example, these sensors here have seen lots of photons, whereas these ones probably have seen a single photon. And then the color encodes the time of arrival of the photons, and so these are earlier photons, and these are later photons. So you can imagine a muon going through from left to right in this image. And so the end resolution is going to be quite poor, and we're going to discuss why that's the case, but about a factor of 2 in the resolution. But the angular resolution is going to be good, better than a degree. And the reason is that you have this long lever arm to be able to figure out the direction of this muon. Neutral current interactions and electron charge current interactions are going to produce electromagnetic harmonic cascades. And those are going to be sort of blobs of light, which we call just cascades. The energy of this is actually can be measured quite well. So the positive energy can be measured about 15%. But the direction is much more tricky because you need to know if the neutrino is coming from this way or from that way. And from this event, by eye, you cannot tell. But I will tell you later that we can figure out this with about 10 degrees resolution. How we do that is tricky. Now, tau neutrinos, this is my favorite neutrino type. It's because tau neutrinos are the least studied of neutrino species. And so in this case, you have a neutrino that comes like that. It hits here. it makes a high energy tau, and it goes some distance, and then the tau disintegrates. So if we have 1 PeV tau, so that's 10 to the 6 GeV tau in energy, that's going to go approximately 50 meters in the ice before it decays. And these sort of double cascade structures or double bank structures can be resolved when the taus have about 100 TeV energy or higher. Okay, so that's how these detectors look, very roughly speaking. So when I say track, I mean this long thing going through my detector. When I say cascade, I mean this. And when I say double cascade, I mean something like that. Okay, and I will use these words throughout my lectures always. And the important thing to remember is track points well, but energy is very bad. Well, it's poor. Cascade, energy is good, but pointing is poor. And double cascade is tricky. Okay, good. So now the question is, how do I design a detector that can see these things, and how do I compute, what do I need to put in together to be able to see these objects, right? Like, how do you determine that you need 1 cubic kilometer of ice? How do you figure that out? So we're going to try to figure that out. Okay. Suppose that this is Earth, and I simplify Earth square now, and this is a detector space. This is my detector. I will instrument it somehow, but this is instrumented. And suppose that this detector has some height L, okay? And so the question is, I want to figure out what is the chance that the neutrino of a given energy will interact in this space L, okay? So that will depend on the size of this object. Okay, so what are the elements involved here? So it's going to be different. So if you have an electron neutrino, your electron neutrino, so you see a dashed line, it means it's an electron, it's a neutrino, sorry. A neutrino is going through, and eventually hits in my electron volume. Like I was mentioning, I can only see the electrons inside of my volume. So I need to have my electron neutrino actually reach there. So that's one case. Then I have another case, which is this one. Oops. Back. Which is this one, where you have maybe a mu neutrino. The mu neutrino, it could interact here, and then I see my muon, but it could also interact here, outside of my detector. These muons are going to go multiple kilometers in principle, and so this muon could actually reach inside of my detector, and I could still see it. Okay. And then you have the tau neutrino. And so the tau neutrino, similarly, could interact outside, and the tau could leave some distance. Is this clear for everybody? Okay. Good. So that means we have two types of problems. In one of them, the electron has to be inside, and these ones actually can range outside. So the first thing I need to compute is the chance that the neutrino actually gets to my detector, because this neutrino has to travel the whole planet, right? He has to go through my planet to get to my detector. So that's given by this. And in this notation, lambda nu is the interaction length of the neutrino. That is the typical length that the neutrino has to traverse to interact. Okay, so this is the chances that happens. Then the neutrino actually has to hit that. So if this is the probability that the neutrino does not interact in this piece, then the chance that it actually interacts looks like 1 minus that. So that then if this length is much more than the interaction length, which would be the case, roughly scales like this. And then I need to figure out what L is. Well, L for the electron neutrino is this length here, it's my detector size. But L for my mu neutrino is actually longer, right? Because it could have been anywhere as long as that muon reaches this blue box here. So for a mu neutrino, the length is going to be the muon range, which is going to depend on the muon energy. which is going to depend on the neutrino energy. Don't worry about what y is for the time being. And then for the tau, well, taus don't lose much energy, but they can decay. So the distance that the tau can travel is the lifetime times the boost factor of the tau. Right? So this is how much a tau can go once it's produced. And then the probability of detection is just this, which is the interaction length times this length here. So that's what we need to compute. Okay, so these are several pieces that you perhaps not have seen before. It has the neutrino cross sections, which maybe some of you know, but maybe some of you have not seen before. It has this muon distance, which you maybe have seen before, and it has this Arguelles probability. So I want to explain you all of these pieces. So let's start with the neutrino interaction probability. Okay? So this is a plot that shows you the neutrino cross-section, and the cross-section is proportional to the probability of a neutrino interacting with, in this case, you can think about it as a proton, as a function of the neutrino energy. And so here is given in energies of electron volts. So we are actually interested in this part here, where it's GeV, TeV, PeV, and extra electron volts in energy. Okay, and you can see important features here is that the neutrino cross-section grows, first with one slope, and there's a second slope, and there's a spike here. So we're going to try to understand this. And what I have drawn here are just different neutrino sources, but what matters for us is this part here. Okay. So the neutrino interactions, at these high energies actually happened between the neutrino and one of the quarks in the proton. Okay? So remember that the energy exchange between particles tells you is related to the distance scale that you're probing, right? So a typical distance scale that you probe is going to be inversely proportional to a typical energy exchange that you have in your process. Now, what you see here is a diagram of a neutrino, we call this deep inelastic scattering. Okay? And it's deep because you're going to the innermost part of the quark, and we'll see what inelastic means in a minute, so why is it deep inelastic. So you're going to have a neutrino or an antineutrino. Let's think a neutrino for the time being. And that's going to hit, for example, a proton. It could also be a neutron. And it's going to hit, in particular, one of the quarks in that neutron, in that proton or neutron, Q. And so what matters is the interaction between that quark and that neutrino. So how should this scale? So let's think about the following diagram. So I'm going to simplify this. I have my neutrino, and this is my quark. Okay? And then this is going to produce, in this case, I have a charge current exchange, so that's going to produce me the associated lepton. I'm just going to make this a muon, so this is easy. And then this is some other quark. Okay? Like that. And so the question is, if this neutrino has some energy in nu, this cross-section of this process, how does this cross-section depend on the energy of the neutrino? Like to what power or what index, and there's probably some constants here. Okay, so that's what I want to figure out. Are there any clues for this? Anybody has an opinion? Okay, good. This could be good. Okay, so, well, you see here, I've simplified my diagram into this blob. And so you see this blob has this W boson, is MW. And if you have taken particle physics, this calculation will look maybe simple. If you have not taken particle physics, this could be confusing, so I'm going to do slowly. So it turns out that the cross-section of a process is equal to what we know in particle physics as the amplitude of that process squared, which I'm just going to call it m. And the amplitude of this process is going to be proportional to these couplings here, which I'm just going to call little g's. Okay, so I'm just going to call G. And it's going to be inversely proportional to the thing that's mediating this interaction. Okay, so that's going to be schematically, if you have particle physics people in the audience, they maybe get angry with me. But I'm just going to call this like this for simplicity. Okay, where this Q is the momentum that's transferring this interaction here. Okay, so it's something like that. So the chance that a neutrino interacts is going to depend inversely to the W boson mass. And this is important because we say that there are 4 fundamental forces in nature. There is the gravity, there's electromagnetism, and there are the 2 nuclear forces. So the weak force coupling, G, but the weak force is weak, rather, because the mediators of the weak force are actually very massive particles. In this case, this is this MW particle. So when the neutrino has low energies, it's going to exchange relatively few amount of energy with this nucleus. So I can think that this thing is going to scale like G4 divided by MW to the 4 power, like that. Okay, so this is in the limit where the exchange of momenta is relatively small. Okay, so that's good. Now, here is something that I always find really useful, and I hope you will find useful as well. So particle physicists like to work in units that are known as natural units, where we express everything in terms of energy. So the mass of the W has units of energy, but length has units of inverse energy. Okay? And time has units of inverse energy too. Okay? And you can think about this because if you remember the uncertainty principle, you can see how length and energy have to be inversely related. Essentially, this sort of first idea we were talking earlier. Okay, so that means that this object here, right now, has energy to the -4 in units, if I do dimensional analysis, because the mass is 1 over the mass to the 4 power. And on the right-hand side, I have sigma, and the units of sigma is area. So this has to have units of energy to the -2. Okay. So you can see that my cross-section, sigma, right now it goes like the mass of the W, which is what's suppressing my interaction, to the 4 power. That's giving me a e to the -4. And then the sigma, which is to be e -2. So this is dimensionally wrong, right? So this doesn't work. So for this to work, I need to have something that has units of energy square. And the right thing to put here is the center of mass energy square. Okay. And the reason is that, why is that the reason? The reason is that you can think that in high energy particles, all of these particles, the quarks and the neutrinos and the muons, are essentially massless. And so the only physical quantity that this interaction has is the interaction energy that we have in this process. And so the only thing that's dimensionally possible here is the center of mass energy square. And so this will go e to -4 times the center of mass energy square. Well, what then you can do is you can compute the center of mass energy of this process. So the center of mass energy is going to be the energy of the neutrino plus the energy of the, let's say, proton square. Okay, like that. And so that's going to be equal to P nu squared plus PP squared plus 2P nu PP. That. Where these are actually the 4 momenta of the neutrino and the proton respectively. And so you may remember that this just gives you the mass of the neutrino square plus the mass of the proton square plus 2 times the energy of the proton, the energy of the neutrino, minus the dot product of the neutrino and the proton 3 momenta. Sorry, it got really, really messy. But my point being is that, well, the neutrino mass we're going to neglect, okay? And we're going to end up with something that then looks like Cm squared. It's going to end up looking like mp squared plus 2 ep e nu. And actually, in our problem, the protons in the ice are actually not moving, which means that the protons are actually at rest, which is just going to give me mp. So this is going to give me then mp squared plus 2 mp e nu. So now, if the neutrino energy is, say, 1,000 GeV, so 1,000 times the energy of the proton, this term is going to be much larger than this one. And so this whole term is just going to be equal to G4 mp E nu divided by mw to the 4th. Okay. So what we have discovered is that as long as the neutrino interaction is mediated by a heavy particle, and the outgoing particles are relatively light, the neutrino interaction probability must be linearly proportional to the neutrino energy. Okay? Are there any questions out of this? Have people seen this before? Yes? Some of you have, some of you not? Okay. Good. So this is a nice exercise for you to recall, and we will actually go back to this question later. I also want you to note that when the energy becomes very, very large, eventually this Q square is going to start to dominate, and that's going to suppress the interaction a little bit. So what we expect is that the neutrino interaction actually grows with energy and then eventually sort of slows down as this Q square term stops it. Okay, good. And if you have not seen this calculation before, I strongly encourage you to try it out. Good. So then you can actually go and measure this in accelerator neutrino experiments. And this has been done. So here you can see the neutrino cross section actually divided by the neutrino energy. So this is convenient as a function of the neutrino energy, and you can see that it's really, really, really flat. But high energies, this actually starts going down and eventually sort of bends a little bit. And the important thing is that we have actually introduced 2 variables here that are going to be relevant, which is this x and this y. Let me tell you what those are in a second. So y here is known as the inelasticity, or inelasticity. Okay. And it's going to be related to the energy of the lepton that's produced of the neutrino interaction. So y is going to be 1 minus the energy of the outgoing lepton divided by the energy of the incoming lepton. Okay. Yeah, who has a question?
By this plot, we can see that the cross-section of the anti-neutrino is smaller, right?
Yes.
Why is that?
Oh, that's a really great question. That's a really great question. Thank you. So the reason is that this has to do with the fact that neutrinos are only left-handed particles. So when the neutrino interacts with a quark, it interacts with the left-handed part of the quark. And so the interactions between the neutrino and the left-handed part of a quark can be, let's say, in any direction, okay, because the spins end up canceling. However, interactions between an antineutrino and a quark have to have very specific orientations because they have to preserve, essentially, a spin has to be preserved in the interaction. So if I were to scatter with, let's say, antimatter this should be reversed. Okay? And so what sometimes we call this is that these interactions are, we say their helicity suppressed. Okay? In that you have to have a very particular orientation of your spin to be able to interact. And so the way, I'm going to draw it, but the way you can see this is you draw a diagram like this, and you're going to sketch it, and you can complete it. You have a neutrino, let's say it's going like that. So a neutrino is a left-handed particle, which means that if the neutrino is going in this direction, its spin is going in the same direction. And now you have to put a quark here, which is also a left-handed particle. So let's say that the neutrino is interaction. The quark, let's say, it's going like that. This is my quark. And so now the neutrino, the spin is going like this. However, if you have the antiparticle, and so you can see that the sum of the spins here is equal to 0 in this process. But if I actually have the antineutrino, because a right-handed particle, the spin actually goes in the opposite direction. And so now you have a total sum of spin that's onto the left direction, which means that there's a preferential direction that's induced now. And so the process only happens preferentially in one orientation. So that suppresses that with respect to the other. Does that make sense? Thank you. That's a really, really good question. Thank you. Good. OK, so good. That's a really good question. So the elasticity is going to tell us the energy that the lepton is going to have. Okay? And then the other part that's important here is this x, which is known as Bjorken x. And that is how much energy, or how much for momenta does the quark carry out of the proton. Okay? So the neutrino interaction is going to depend, this is the actual formula, on the energy that you give to the muon or to the electron, and then the energy that you hit, or the energy that you take out that quark. And here they enter these things here. These things here are known as structure functions, and there are parametrizations of the distribution of momenta of the partons within the quark, within the proton, sorry. Okay, and these are measured in laboratory experiments. Questions on this? Okay, good. So those parton distribution functions are really well known because those are measured in experiments that measure electron-proton collision. When you measure electron-proton collision, you can also obtain the same distribution of parton momenta in the protons. And so you can see here more or less the errors that we expect. So in the regions of tens of TeVs, the error on the cross-section is more or less at the level of 4%. Okay? Depends on who you ask for a little more. So it's relatively well known. Okay. Now let me tell you something that's fun. Is something that was predicted many decades ago, which is known as the Glasgow resonance. And it's the following process. So it's the case where you can have a neutrino interacting with a W, or making a W. So how does this work? So I'm going to draw this diagram again. So you're going to have an electron antineutrino that's going to hit an electron in the atom, and that's actually going to make a W boson like that. Okay, and then the W boson is going to disintegrate. We'll talk about what it disintegrates into in a minute. But it's actually going to be an on-shell W boson. So what should be the condition that I need to put in so that the neutrino produces this W particle for real? What people think should that condition be? I saw some people raise their hand before, so some people have taken particle physics, because some people knew what I was talking earlier. So somebody must tell me, what is the condition that I must put so that the neutrino has enough energy to make that W particle, as we call it, on shell. So it's a real W particle that's produced. How do you figure out the minimum energy for it to happen? The mass of the W, okay. So what must it be equal to the mass of the W? Good. So the center of mass energy must be equal to the mass of the W, okay? So the center of mass energy, I'm going to do it square because I actually only know how this equation if I square things out. It's easier if you do it like this. So that will be the 4 momenta of the electron plus the 4 momenta of the neutrino square, okay? And I'm going to make it a little more precise. So the 4 momenta of the electron is at rest, so it's just the mass of the electron and no 3 momenta. And the neutrino, I'm just going to assume it's massless, so it has some neutrino energy and some momenta in such a way that the momenta is equal to the energy. Okay? And so if I square this, I get that this is Pe minus square plus P nu E square plus 2 Pe minus dot P nu E. Right? And so this gives me now the mass of the electron square plus the mass of the neutrino square plus 2 times, and I do this product, which gives me E nu Me minus 0 dot P. And so I end up having, well, the mass of the electron square plus the mass of the neutrino square plus 2 times the mass, the energy of the neutrino Me. The same thing we had before with the proton. So the mass of the neutrino, in all of these lectures, except when we talk about neutrino oscillations, we can set to 0. So this is 0. And the mass of the electron is also very small compared to its energies. 0. So we get that this is just 2 Me, and this has to be equal to mw squared. So what you do is you solve for E nu is equal to mw squared divided 2 Me. Okay. And you can plug in those numbers, and you will find out that this ends up being about 6.4 PeV. So that's 10 to the 6, or if you want to be, 1 PeV is 10 to the 6 PeVs. Okay? So that's the energy you get. Any questions on this? So once my neutrino hits that energy, when it hits that energy, it can really make a W, as we call it, resonantly produced. Questions on this? Okay. One of the things that's really annoying about this Keynote's tablet thing is when I click next, everything disappears. So if you have a question, ask it now, because if not, I have to rewrite everything. Okay, no questions. Wait, history. So there you have it. This here is the so-called glass resonance. Is the cross-section, and you see, because it produces a real particle, it's actually enhanced. So here you have the neutrino making neutrino nucleon cross-section, the anti-neutrino one, which is here. Then you have the W production, okay, which is this glacial process. And so this is given by this formula here, where Y is again the energy related to the energy that the outgoing particle has. Okay. So one thing that's important about this process, or why do I mention this, is because the Earth only has because the Earth only has electrons, this only happens for electron antineutrino. If the Earth had like muon atoms, like muons around it, it would also happen for muon neutrinos, but we don't have that, right? And there's no antimatter. So then this only happens for anti-electron neutrinos. So this is going to be important for flavor identification, right? To be able to understand the relative contributions of neutrinos to antineutrinos. And what happens when you produce a W boson? Well, this is how a W boson disintegrates. So W boson disintegrates about 10% of the time into each of the leptons, and then about 70% of the time into hadrons. Why is that going to be important? When it's going to disintegrate into hadrons, it's going to make a shower that typically is going to be contained in my detector. That means that 70% of the time the W boson is produced, all of the energy is contained within the detector volume. So if I measure something that has 6.4 PeV of energy, that's most likely a W being produced in this process. Okay? Cool. There are other subtleties to this process, and the subtlety is that electrons in atoms are not really, at rest. Electrons are really moving around in orbitals, right? So they have some little energy, and that actually causes distortions in the cross-section of this, which was computed by Lowy and Glashow some years ago, these sort of small corrections. And there are other corrections related to the Glashow resonance that have been computed more recently. This should be actually, this should be 22 actually, not 20, No, this is fine, this is fine. And this is related to things that says Glashow resonance improved. It includes things that are more complicated, and what are those more complicated things? Well, there are things like, for example, this is supposed to be a wiggly line. Things like this electron emitting a photon. And so you say, well, why is that important, right? Well, you see here, this is the calculation, let's say, naive, and this solid line is better. Okay. And you see that the better and the naive are identical before the spike, but after the spike, the better one is higher. Why is that? Because after a spike, the neutrino has too much energy, sort of like overshoots. But if that electron is able to wiggle out some energy before it hits, it matches quite right, and it increases the rate, right? So these effects are of the order of, 10-ish, well, 50% after it, but something that now we're starting to worry about. Okay. So what about the flavor dependence of the cross-section? So we have talked about the cross-section, it increases with energy, it grows, there's this Glashow, so obviously the Glashow, because of the air content, there is only antineutrinos, sorry, only pressure antineutrinos. What about the flavor dependence? Well, it turns out that the cross-section is going to be approximately it's going to be suppressed, for tau neutrinos. And the reason is that tau neutrinos need to produce a tau, which is much more heavier. And this produces suppression of the cross-section. This suppression starts to become small somewhere around, a TeV or so. But at lower energies, it becomes important. Okay. So now, let's see if I have time for this. So I have time. Okay. Oh, let's talk about this. Okay. Good. This actually goes to one of your questions. So this is the neutrino energy. Okay. This is the average inelasticity. Now remember that inelasticity for us is related to the energy that the outgoing lepton has. So remember that Y is 1 minus E out over E in, right? So if I have a neutrino, comes with E in, and a muon comes out, that's E out, okay? So on average, if the Y is about 0.2, that means that 80% of the energy goes to this outgoing particle, right? Okay, so this is the interpretation of this 0.8. 80% of the energy goes into this outgoing lepton. So now, let's go back to the question that one of your peers was asking earlier. Notice that at lowish energies, below a PeV, the antineutrino cross-section is a smaller neutrino cross-section. However, at higher energies, the cross-sections are identical. Can somebody guess why that's the case? Guillermo, we just talked some minutes ago. Somebody must give me a guess, if not, we're moving ahead. So we were saying that before, remember that this has happened to do with the quarks and the spins of the particles. Okay. No guesses. So when you have, so what's a proton made of? Can somebody tell me what's a proton made of? What quarks? Ups and downs, right? So it's made of ups and downs. And what are those quarks typically called? They're called valence quarks. Okay, so those are the quarks that have the most momenta of the proton. However, if you look deeper into the quark, what happens? Sorry? Speak up. Parton distributions, but what are these parton distributions? What are they? What's produced? Quarks and gluons. Okay, so if I go deep into it, I start seeing quarks and gluons. And in fact, what happens is that you have this sort of sea of gluons that are splitting into quark-antiquark pairs, right? There is this soup of quark-antiquarks that are forming inside of the proton. So if you look very, very, very deep into the proton, you see this quark-antiquark soup, okay? And so what happens is that at very, very high energies, the neutrino is interacting with the quark or the antiquark. And so because there are equal amounts of quark and antiquark in the C-quark contribution, now there is no longer a suppression that we had earlier. So here, this is suppressed because interactions happen with quarks, because these are the valence quarks. But here, interactions happen mainly with the C-quarks, which are actually quarks and antiquarks. So now it's symmetric, right? So now matter and antimatter are symmetric, whereas earlier they're not so symmetric anymore. So this is, again, the reason we were talking earlier. Is this clear for people? Yeah, it's a transition that's continuous. In fact, this is just the average in elasticity. It's sort of like smooth transition. As you interact, as you have higher energy, you are more likely to interact with the C quarks and less with the valence quarks. Or the chance, the C quark population is more likely to be your target than the quark population. Okay, so it's something that, it's a continuous transition, essentially. Okay, so it's not really like a hard boundary here. There is, let me say it another way. There is always a contribution from the valence quark. Usually the contribution from the C quark is larger and larger and larger and larger, so that the contribution from C quark just becomes negligible. Okay? Cool. Okay, so, but what I want you to remember is that the lepton that comes out of the neutrino interaction is relatively high energies. Okay? Oops. No. And if you have to remember something something that you write in a piece of paper that you can review forever, are these equations here. This is approximately the neutrino nucleon interaction with materials, with neutrino with a nucleon. This is the neutral current charge current interactions, and this is valid in this high energy regime. Okay, so that has what I want to talk about how neutrinos interact. It took me too long. And so now we have to talk about how long the neutrino survives, okay? Do we have time? Can I he says we have time, so we keep going.
We have about 20 minutes.
Oh, wow, plenty of time. Okay, what is this? So, what I want you to do is something relatively, I hope that you can do it with the person that's sitting next to you. Everybody has a person next to them, right? And a piece of paper. Okay, so suppose that these are the neutrino cross sections. Take the top one to simplify this. Suppose that the Earth is made entirely of 5 grams per centimeter cube. It's a blob, okay? My question is, what is the interaction length of 100 TeV neutrino? How do you compute that? Can somebody tell me? So what is the length that the typical neutrino will interact in a medium that's 5 grams per centimeter cube if the neutrino has 100 TeV of energy? How do I compute that? Okay, so the interaction length. I'm going to write here. The interaction length is going to be, is it going to be proportional or inversely proportional to the cross section? Inversely, what is it? You said inversely or proportional? Inversely proportional, thank you. And is it going to be proportional or inversely proportional to the density of material? No, inversely. Because the more material, the shorter the interaction length. Okay? The lighter the material, the more it can travel. Okay? So the interaction length is going to be the number density, it's the number of particles per centimeter cube times sigma minus 1, where this is the interaction, which is in centimeters squared per particle, which is given by this equation here. And you need to know that 1 gram has Avogadro number protons to first order, and I will give you 4 minutes in pairs to figure out what that number is. So talk to the person left or right, 4 minutes, what's the interaction length that you need? Everything that you need is on this slide. Go. Yeah, thank you. Yeah, because I don't know. But if you could refill it or...
Yes.
Thank you.
I think I can go back in and out in 3 minutes. By the time I come back.
Yeah, perfect. Sorry? Where? Sí, Avogadro number. Sorry. Gracias, thank you. Okay, do we have somebody has order of magnitude? Ten to the 11? Ten to the 12, 10 to the 11? What number do you get? 10 to the 11? Okay, that's all right. I think that, so 10 to the 11 or 10 to the 12 centimeters, it's about 10 to the 6 kilometers, right? What's the size of the Earth, right? Size of the Earth is like 10 to the 4 kilometers, right? So that means that these neutrinos will go through. So here I have, this is actually for an old cross-section calculation, so numbers are not quite the same as yours. This is actually for centimeter water equivalent, so this assumes 1 gram, not 5. That's why this is lower. But more or less, if I were to have just water, and I had, you know, we said 100 TVs, right? So we should be somewhere on the 10 to the 10, well, if it's more dense, it's higher, right? So it's certainly longer than the diameter of the planet. So the Earth is actually transparent to neutrinos below 10 to the 4, below 40 TeVs. But then after that, because this cross-section, which I already, this here, because this cross-section scales with this 0.3 e to the 0.3, it actually is going to make my interaction length go down. So you can see it in this figure. So here interaction length is decreasing. Somewhere over here, it crosses the diameter of the planet. This exact crossing depends on the exact crossing calculation that you use. And so somewhere around the tenths of TeVs, you start, you know, really crossing the planet. So if I were to give you a different cross-section, you could figure it out. And so one thing that's also important to note is that if you have an electron antineutrino, because it has this glass horizontal enhancement, that actually essentially never crosses the planet, because the cross-section is huge, okay? That's essentially opaque, okay? Good. So that's how we compute the transparency of the Earth. The transparency is computed by this suppression. And so one thing that's interesting is that we typically talk about isotropic neutrino fluxes. So it's sometimes useful to talk about the direction average transparency of the planet. And my detector is looking at all directions. So what's my average transparency? So that's known as the shadow factor. And the shadow factor is just the angle average factor of this thing you have computed, which is it's actually interaction length divided by how much material you're going through, right? So this is what you have computed. This is your interaction length, okay? And then this is how much material you're going through at each distance. And so if you compute that, you're going to get that the average attenuation of the neutrino flux over all directions is given by the shadow factor. And so you can see that the shadow factor is, so most directions are transparent, still at 100 CV. If you go to the core, then that's bad. But if you go through the mantle or so, you're still mostly transparent. If you start going at higher neutrino energies, because the cross-section keeps growing, eventually you are starting to get attenuated, okay? So at high energies, neutrino detectors are essentially horizontal detectors. Right? If I have high energy neutrino observatory, I only see in these horizontal directions where there is little material. At low energies, by low energies I mean below 50 TeVs, I can see any direction I want. Okay? So I have all sky vision below approximately 50 TeVs, and I have vision at lengths where there is little material at distance at high energies. Okay. But it's more complicated than that, because neutrinos have two types of interaction. So how does this work? So suppose that this is the Earth, right? So here is my detector. Okay. So here is my detector, right? And you have this neutrino. It's coming along. Okay. So two things happen to your neutrino. Your neutrino can go and it can scatter, and it can have a charge current interaction. This is a random process. It could be either of these interactions. So let's say that it has a neutral current interaction. So neutral current interaction, if you remember, is like this. Neutrino comes in, neutrino comes out, and then quark comes in, quark comes out. Okay? And there is also an average Y for this, right, which is comparable in magnitude to the two other cases. So when you have a neutral current interaction, the neutrino is going to come in, and it's going to lose a little of energy, and then it's just going to continue. So that's fine. That neutrino just lost some energy, but I still got my neutrino. Now, there is another possibility, which is that my neutrino is coming along. Oops. What did I do? Oh. We continue tomorrow? Sorry? Continue tomorrow then? Does that mean that? Yeah, I'll finish this point and then we can. Just a second to depend on the. It's restarting, I guess. I guess it's. Okay. We're back. Okay, so the other chance is you have this neutrino, okay? And your neutrino comes along, it's traveling us along. Let's say it's an electron neutrino. So, some of you may know that neutrinos change flavor as they travel. We will talk about that later, but for this discussion, they do not. Flavor doesn't change. Let's keep that like that. And it will not be a problem, don't worry. So the neutrinos, this electron is going along, and then it has such current interaction here, okay? And so now what produces an electron? But now I have an electron in rock, you know? This electron is going to immediately start losing energy in that rock. It's going to lose energy electromagnetically. It's actually going to produce an electromagnetic cascade in that rock, and it's just going to die. You know, for all purposes, that electron is gone. So that neutrino is lost. This neutrino is absorbed. Okay? So that neutrino is absorbed. Now, if I have a muon, well, you know, we talked about this briefly earlier. If you have a muon, and if you are lucky, and your muon hits here, then you could see that muon. Maybe you see that muon, maybe not. Depends how close it happens. We will talk about that more in detail tomorrow. But if that muon neutrino comes along and it hits here and makes a muon, that muon typically is not going to interact. The muon distance is typically going to be ordered tens of kilometers at best. So it's never going to be 1,000 kilometers or 100 kilometers. But then something happened which is interesting, and this is the reason I'm making this whole story here, is what happens when you have the third neutrino flavor. So now, let me just, oops, no. Okay, so let me just go here, and let me make this a tau neutrino here. And now let's say this tau neutrino hits here, more or less in the center of the planet. It decides to have a charge current interaction. It happens randomly. Right? So now a tau is produced. So a tau is a very short-lived particle. So the lifetime of a tau is about 10 to the minus 13 seconds. Okay? And if you have, and the mass of a tau, if of order 1.7 GeVs, okay? So if you have, let's say its neutrino is 100 TeV, so that's energy of the neutrino is this much energy. So the most energy this tau can have is 10 to the 5, which means that the boost factor is going to be order of 10 to the 5 in order of magnitude. So that means that the lifetime in the lab frame of this particle is going to be something of the order of 10 to the minus 8 seconds or so. Okay. 10 to the minus 8 seconds, it still means that that particle is going to go order, meters, right? It's not going to go tens of kilometers. So this tau still is going to go only order meters. And it so happens that and we'll talk about this tomorrow, the energy losses of taus is very small. And so what happens is that this tau here disintegrates very promptly. So the tau disintegrates here. But when a tau disintegrates, it always has to produce, no matter how it disintegrates, it always has to produce another new tau. Okay? We will see why that's the case. But why is this important? Is because we have actually discovered something interesting. So electron neutrinos, they only can be seen when they're very close to us. Mu neutrinos effectively in Earth scales the same. But the taus actually are interesting because every single time that a tau neutrino interacts, it produces a very short-lived particle. And the tau that's produced out of this is relatively high energy. What this implies, and this is the important part of this slide, is that the Earth is effectively transparent to tau neutrinos. Okay? So this suppression of the direction of the neutrino interactions is mostly for electron and mu neutrino flavors. For tau neutrino flavors, because of this effect here, the Earth is going to be mostly transparent. And so this thing here is known as tau regeneration. And it's very important because that means that if you're looking through the planets at very high energies, the only thing that you should go through essentially are tau neutrinos to first order. Okay? And the reason is this short-lived particle that decays promptly. Okay. So any questions on this? Okay. So this is something that you can actually compute. This is, you can go and solve these equations. So what you do is you write an equation like that. This tells you the evolution of neutrinos as a function of distance. This is actually in column density, but this is distance to first order. And this term here is your absorption of neutrinos. And then you have something that describes these reinteractions because of these undercurrent losses that depends on the neutrino interaction probability, which is this thing here. And that gives you things like this. So it tells you that, for example, if you have an air crossing trajectory and you have this sort of spectra, you can see that they're all very much the same. But if the spectra is harder, which means there are more high in the population, you can see the tau neutrinos, which is the blue ones, are a little higher. And this is this effect that I'm talking to you about. Okay. And how much regeneration you have is going to depend on the spectral index of the particles. So you can see it better in this plot here. So you can see this is an e to the minus 2 spectra, minus 1.5, minus 2, minus 3. And this is the fraction contribution of secondary neutrinos that come from ray interactions. Okay. This is another way of thinking about this. Here, on the plot on the right, if you have never seen this, this is the Earth density profile. This is the center of the planet. This is the crust. This is the mantle, the outer core and the inner core. And this is more or less the error on the densities that we know them from seismologic measurements. And so this is the density. So the core of the planet is about 12 grams per centimeter cube. And here the crust, somewhere around 2 grams per centimeter cube. And so now you can look at what that means in terms of the absorption. This is the absorption at different energies. And you can see that the electron and the muon are the same line, but the taus are a little higher because of this regeneration effect. And you can see that as a function of this angle is known as the zenith angle, where cos theta of 0 means cos theta of 0 means this direction, and cos theta of 1 means earth through-going. Okay, so you can see that, for example, at 10 TeV, if I go through the core, 60% of them survive. However, if I have like 500 TeV, essentially none of them survive. Okay. And so you wonder, if you could do something neat about this, because what I could do is I could go and I could measure the transmittance of neutrinos at every direction, right? And you could ask yourself, if with that, maybe you could measure the Earth density and the Earth core with that. And then the answer is yes, you can do that. And this has been done. Here, there is extraction of the Earth density using neutrino transparency measured by IceCube. The errors are really large, but this is what people expect to do with 10 years of data, which is what we have right now. This is actually Monte Carlo, the black, right? And what is neat is that, well, at least I think this is neat, but is that, how do we know the weight of the Earth? We know the weight of the Earth because of gravitational interactions, right? That's how we measure the weight of the Earth. But this here is measuring the planet mass using weak interactions, which is, I think, really, really, really cool. And it turns out if you do this analysis, you end up with about the correct mass, which tells you that, if you think that there is an empty hole, maybe of dark matter in the center of the planet, and there are people there, whatever, this doesn't work. Okay? Good. So I've run out of time. So tomorrow, I want to talk about how long do muons and electron taus can go through. We'll talk about muon ranges and muon losses, and how we reconstruct neutrino events. Thank you. See you tomorrow.
So, any more questions for Carlos before we go for the coffee break?
So maybe I am a little confused, but when you show, I think, the derivative of sigma to respect to x and y, why? There are some there are some f functions. Maybe I am confused, but for me, it remembers the functions that appear in electric precision tests. Is that right, or is just other thing?
Sorry, what do you mean? So this function F1, F2, and F3, those are different ways of, so this F1 and F3, they parameterize the parton content of the quark, of the protons already.
Okay.
So they have a Q-square dependence because essentially you can think that the proton at different scales, which is measured by the energy exchange, Q-square is the energy exchange, so at different magnification amounts, if you want to think about it, the distribution of momenta of the parton looks different, right? This is why these functions here depend both on Q squared and in X. Is that your question? I'm not sure if that was your question, though.
Oh, yes, yes. I was confused.
No problem.
Thank you.
Other questions? Sorry? Yeah, these are form factors. Yeah, these are form factors. Yeah.
Whoa. So from that globe that from the Earth, and then the various types of neutrinos that can pass through it and different interactions that we have. So essentially, the electron neutrinos we can only see through neutral current interactions.
So the electron neutrinos, that's right. So an electron neutrino will get to you only if either it did not interact through the Earth and only in your detector, or if it had only intercurrent interactions along the way.
Okay, so
the same is for mu neutrino, in principle, if it interacts just as your detector, you could also see that.
Yeah, but if I have like an electron neutrino come with a really small zenith angle, then it can interact really close by and then relate an electron in a cascade, then you could detect that.
That's right. So those are going to be essentially interactions that are where the showers are. So as long as, so the interaction happens at some distance, and the light has to travel from that position to the detector. So the distance that the interaction can happen has to be the length that the light can travel, which is going to depend on the ice or the water. It's going to be orders of hundreds of meters.
Okay,
but if an electron neutrino interacts 2 kilometers away, you're not going to see it.
Okay, thank you.